Last time we discussed, starting with algebra, some of the math review we'll be doing. We went over, of course, basic algebra, quadratic formula, and systems of equations. So just to review a little bit, quadratic formula says given an equation ax squared plus bx plus c equals 0, x, the value of x, the solution, is given by the formula minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. And so, generally speaking, if you run across an equation that's quadratic, don't try to factor it. Just put it into the quadratic formula, and it'll give you your two answers. As a physicist or an engineer, you're going to look at those two answers, and you're going to figure out which one is the real world answer. Because if this problem were something like you throw a rock off a cliff that's 10 meters high, you throw it at an angle of 30 degrees with a speed of 20 meters per second, and you want to know at what time the rock will hit the ground. How long will it be in the air, basically? Well, you're going to get an equation that's quadratic in t, so it'll be t squareds instead of x squareds. And so you're going to use a quadratic formula, and at the end of the day, you'll get 2 times. Well, obviously, if you do this in the real world, you throw the rock, it'll only hit the ground at one time. Forget about bouncing. It's not going to hit the ground and then 10 seconds later hit the ground again for no reason. It only hits the ground at a single time. So you have to be able to look at the answers given by this formula and say, of the two answers, this is the actual answer I'm looking for. The other answer doesn't make sense. For instance, as you'll see when we do the problem later, one of the times will be negative, and one of the times is positive. Well, negative time, first of all, doesn't make sense, but even if you try to make it make sense, what it's telling you is, since you started on a cliff somewhere up in the air, the formula is smart enough to assume you actually threw it from the ground, and so you're just starting the problem up in the air. And so, when was it at the ground before you threw it? That's what the negative time would be. But of course, in the answer, you don't care about that time. You just want the actual time moving forward. How long will it take to hit the ground? So just make note of that when you're going to be given or getting two answers to a problem. Likely, there's only one real answer, and it'll be up to you to make sure you know which is the real answer and which is not. Generally speaking, it'll make intuitive sense. It won't be like, well, one answer is 3.4 and the other answer is 4.1. Well, how the heck am I supposed to know which one's the right answer? It'll be more like one's a negative time and one's a positive time. Obviously, you take the positive time. And the other big thing was the systems of equations. And so given, ax plus by equals 0 and cx plus dy equals 0, where a, b, c, and d are just numbers, and you want to solve for the variables x and y, how do we go about doing it? And I said I use a substitution method. Substitution, and what it says is, first, take one equation and solve for one of the variables. So for instance, maybe take the first equation and solve for x. That'll give you x equals blah, blah, blah with a y in it. Second step is substitute that variable into the other equation What's going to happen when you do this is you'll be left with an equation that's longer and more complicated looking, but it's all one variable in it. That allows you to solve for the second variable. Okay, you get an answer, one of the answers. Once you have that, now substitute this answer into the first equation you used. Okay? So you take the first equation, solve for x. X equals something. Take that x, plug it into the second equation. You now have an equation for y. Blah, 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 y is everywhere. Solve that thing for y. I now have y equals a number. Good, that's one of my answers. Take that y equals a number, put it back into the first equation. You now have an equation which is x's. Solve that for x. You now have your other answer. So that's a nice basic, probably the least thinking way of solving this style of problem. As you progress later on and do more math, you're going to learn, even in my physics courses, like for instance, I teach statics and dynamics, which is physics 310, and I just taught them how to solve this type of problem using linear algebra, using what's called matrices. It's a completely different method, more fancy looking, but at the end of the day, you get down to x equals a number, y equals a number. So there will be more techniques later as you learn more math, but for now, this is perfectly legitimate. It works for the types of equations we're going to have. We're not going to have big old huge, 10,000 equations with 10,000 unknown type things. 2 or 3 is what we're going to be dealing with. Usually just 2. So that's what we did last time. Now what I want to introduce, that's everything about algebra. What I want is to get into trigonometry. This is going to be a very important piece of mathematics to understand for physics. And like I said in our previous lecture, the reason is we're trying to get to what's called vectors. Vectors is kind of this abstract thing people made up that allows us to solve problems and give information better, more easily. But in order to get to vectors, you have to know about trigonometry because the math of vectors is a little different than the math for regular numbers. So what's trigonometry all about? Obviously, it's kind of in the name. Tri is sitting there. It's about triangles. So it's all about triangles. When you take trigonometry in a math course, you can deal with any kind of triangle. It could be a right triangle, it could be scalene, it could be isosceles, whatever. Any triangle, there are methods of figuring out pieces of the triangle using math. And the basic concept goes like this. Given some triangle, if I know this angle and I know this side, and maybe I know this angle too, can I figure out the other pieces of the triangle? The other angle, the other two sides, stuff like that. That's the kind of thing trigonometry is helping us do. Now what we need trigonometry for in physics is going to be the right angle stuff. So we're not going to worry about general triangles. General triangles usually means you're using law of sines and law of cosines. We won't worry about that. What we're going to deal with are right triangles, which is a special case. And so the special case of right triangles takes law of sines and law of cosines and makes it a little easier for us. So, first thing to know is every triangle we're going to worry about will be of the form one angle is always 90. That makes it a right triangle. And the side that's opposite to the right angle is always called the hypotenuse. Okay? And it happens to be the largest side. The reason it's the largest side is because it's the side which is opposite to the largest angle. The bigger the angle, the longer the side will be. The smaller the angle, the smaller the side will be. So for a right triangle, the biggest angle in a right triangle is 90. So we're going to have the longest side is the side which is opposite to 90 degrees. Okay. And one thing we know, probably the most famous thing we know about right triangles, goes like this. If we have this side here and this side here, and I'll just label them X and Y for now, there's a relationship between how long these sides are. And the relationship goes like this. X squared plus y squared, so the length of the x side squared plus the length of the y side squared will give us the hypotenuse squared. This is, of course, called Pythagorean Theorem. You usually see it a squared plus b squared equals c squared, where they're calling c as the hypotenuse, a is here, and b is here. It's the same thing. It's just different variable letters, you know. The relationship is what's important. The square of the longest side, called the hypotenuse, is equal to the sum of the squares of the other two sides. It's the most confusing way to say it, but that's what it says. That's the first big thing you need to know. Pythagorean Theorem. The side lengths are related to each other. What else do you need to know? Well, of course, there's another relationship, and that relationship is about the angles. So if you call this angle theta and this angle phi or phi, then there's a relationship between the angles of a triangle, and it says that the sum of all angles, of all interior angles, let's say, of a triangle equals 180 degrees. Always. If you add up the three angles inside a triangle, they always add up to 180. Okay? Now, if I were going to be a technical mathematician, I would have to put a little asterisk next to that and say, this is true on a flat geometry. So, if we're on the surface of the Earth, which is round, so it's curved, not flat, and I draw really, really big triangles, and I add up the angles inside those triangles, it will not add up to 180, it'll add up to something different. But on a flat piece of paper and things like this, what's called Euclidean geometry, the sum of the angles is 180. That's all we need to know. So if we look at our triangle here, what that means is theta plus phi plus 90, which is the third angle, is always equal to 180. Another way of saying it is theta plus phi must add up to 90 degrees. Right? Because 90 is already there with the right triangle part, so the other two angles must add up to 90. All right, so those are two big relationships we have to know. Pythagorean Theorem relates the side lengths, and the angles are related by they all add up to 180. All right. Let's move forward and get more trigonometry. The next big thing, I guess, would have to be Sohcahtoa. Sohcahtoa. Now, this is how I learned it in school. I got to college, and as I was going into higher and higher level math courses, I had a friend who was a Chinese guy from Honduras, and he let me know that they did not learn in Honduras math courses Sohcahtoa. They learned some other way of remembering this stuff. So maybe some of you have not seen Sohcahtoa. Maybe everybody has seen it. I'm not sure, but I'll explain it. This is again a relationship. It's a series of relationships, actually 3, that relate angles and sides of right triangles. And so it goes like this. Take the first part, which is the SO part, S-O-H. What that says is the sine of the angle theta is equal to the side opposite to the angle theta, called opposite, or O, divided by the hypotenuse of the triangle. So that's your SO part, sine, opposite, hypotenuse. Sine of theta is the opposite side. And remember, when I say opposite side, you start at your angle theta on my triangle, and I look at the side which is opposite to it. Adjacent would be the side next to. Okay? So that's the first one. The SO part of Sohcahtoa relates sine of the angle to the opposite side and the hypotenuse. The next part, the ka, says cosine of the angle, theta, is the adjacent side over the hypotenuse. So very similar relationship, except now, instead of the opposite side, we're looking at the adjacent side. And adjacent, again, means next to, the one right next to it. And then finally, the last part, the toa part, says the tangent of the angle theta is the opposite side over the adjacent side. And those are the 3 big relationships between the sides of triangles and the angles themselves. And basically, with all 3 of these things, the Pythagorean Theorem, the angle relationship, and Sohcahtoa, any right triangle you give me, if you give me a certain set of information, I can find everything else about the triangle. And that's usually what we try to do with trigonometry. Most of the class is based on, here's a triangle, I give you some information but not everything, and so it's a puzzle. Can you figure out everything else? What do you need to know? What do you need to relate? And you use these relationships as a puzzle to try to figure out all the other missing information. And of course, the course goes more into detail with a lot more relationships, like the double angle formula. And, so if you have sine of twice theta instead of sine of theta, what does that equal to? How does that relate to angle itself? And we won't be getting into that stuff. This is all of trigonometry for us and what we're going to use in this physics course. So, let's take some examples. Let's check out some examples. Let's say we have, let's say we have this triangle here, example. Let's let this be 3, this be 4, and yeah. So, given this information, what do I want to find? I want to find this thing. I'll call it R, just arbitrarily. Let me do it in a different color so it's easily seen what we want. R. I want to find theta, and I want to find phi. Okay, so how can I do this? Well, we have our 3 relationships we could try to do. So let's look at the inside relationship first. Can we use the sum of the angles is equal to 180 to solve for these angles? Well, I have one angle, 90 degrees. That's already sitting there. But the other 2 I don't know. And all I know is that if I add them together, I get 90. but I don't know if 130 and 160 or is 120 and 170. I don't know. So I can't use that relationship yet. What else do I have? Pythagorean Theorem. Pythagorean Theorem would say, if you give me two sides, I could give you the third side. In this case, I have two sides, so I could get the third. Perfect. So let's use Pythagorean Theorem. Pythagorean Theorem says that the side of 3 squared plus the side 4 squared should give me the side r squared. Okay? It's always the two smaller sides gives you the longer side. And the longer side is always a hypotenuse, the side opposite 90. All right, so this is solvable. One variable sitting there, one unknown, so let's do it. We have 9 plus 16 is equal to r squared. So that says 25 is equal to r squared. But I don't want r squared, I want r, so I take the square root of both sides. And I get that r is plus or minus 5. Of course, we have lengths of triangles here, so it doesn't make sense to say a negative 5 length. So the answer is the hypotenuse is 5. And of course, if you're still remembering trig class, they usually force you to remember some of these special triangles, and one of the special triangles is what's called a 3, 4, 5 triangle. And so what the 3, 4, 5 triangle thing means is if one side is 3 and the other side is 4, and we're talking about the smaller sides, then the big side has to be 5. And what's nice is not only is that true, but also if I had another triangle where one side was 6 and the other side was 8, I could use the same relationship. Notice 6 is 3 times 2. 8 is 4 times 2. Well, here's a 3 side, here's a 4 side, so this one must be 5 times 2, which is 10. And indeed it is. So not only is it 3, 4, 5, but the multiples. So 3 times 2, 4 times 2, 5 times 2. 3 times 3, 4 times 3, 5 times 3 also work. But if you don't remember the special triangle, no big deal. Pythagorean Theorem gives you the answer automatically. There you go. So now I know r is 5. But what about my angles? Well, I'm going to have to use one of the trig functions because that's the only thing that relates angles and side lengths. So which one do I want to use? Well, if you look at them, any of these will work because the sine of theta, if I want theta, let's say, sine of theta is opposite over hypotenuse. Well, I know the opposite side and I know the hypotenuse side. So that'll work. Cosine, adjacent over hypotenuse, I have both of those, and tangent as well. But I'll give you a hint, and this is a hint you should use not just for school, but when you actually go to work, if you're going to be an engineer, or if you're going to be a physicist, or some kind of scientist. Take this to heart. If you have the ability to solve a problem only using the data that was given to you, that you know is right, then use only that data. And what I mean is, in this case, I could either say sine theta is 4 over 5, cosine theta is 3 over 5, or tangent theta is 4 over 3. All three will give me the same answer. However, this 5, which is a hypotenuse, I know it's 5 because I calculated it. But I'm not perfect. I may have calculated it wrong. And if I calculated it wrong, then 5 is not the real number. But if I use 5, then that means theta is going to come out wrong too. However, this tangent one, I use what was given in the problem, 4 and 3. And it has nothing to do with anything I calculated. So if I use that one, then I know if I do it right, the answer will be right. So, although in this case I know 5 is the right answer, so it doesn't matter which one I use. But when we're talking about in your career, you're an engineer and you're working a whole bunch of problems, you're calculating a whole bunch of stuff. Well, if you mess up calculating at the beginning and then you use that information for every other calculation you do, then everything you do will be wrong and you have to start over. But if you mess up at the beginning, but a lot of the other calculations you do don't use that information, then those other pieces of data are fine. You don't have to change them. You only have to change where you made a mistake. So there's a tip. Because of that, I'll use the tangent in this case. So I'll use TOA, tangent of theta, is opposite over adjacent. Opposite, so if this is theta, the side opposite theta is 4. The side adjacent, the side next to, is 3. Okay. But notice, I don't want tangent of theta. What the heck is tangent of theta? I don't want that. What I want is theta itself. So now all I have to know, mathematically speaking, is how do you get theta out of tangent theta? So the way you want to think about this, if you don't already know how to do it, is to think about this other problem. Say I gave you the problem 5x equals 10. And I want you to figure out what is x. Well, everybody knows how to do this. Everybody says divide by 5, both sides. Why, though, does that work? The reason this works is because what's going on is this statement on the left side is an operation. It says take the value of x and multiply it by 5. But you don't want that. What you want is just the x by itself without multiplying by 5. So, to get the x by itself, what you do is you apply the inverse operation. This is the formality. The inverse operation basically cancels out the original operation. So in this little yellow example, the operation is multiplying by 5. The inverse of that is dividing by 5. So if I divide this by 5, then I'm multiplying a function or an operation by its inverse. They cancel. But I have to do it to both sides, and so I could get my answer. Well, the same thing holds true for a tangent. Tangent of theta is just an operation. It's a function. I take theta, I apply the tangent to it. If I don't want that, if all I want is theta, then all I have to do is take the inverse tangent operation. And the way we write that looks like this. Tan minus 1 of theta. So I apply that to the left side, and by applying the inverse tangent to the regular tangent, they cancel. There's no theta here. But, again, whatever I do to the left side, I have to do to the right side. So I will do the same thing over here. I'll apply the inverse tangent function to the right. And so I get my answer. Theta is the inverse tangent, or arctangent, of 4 over 3. And if I stick that in my calculator, I see inverse tangent of 4 over 3 gives me 53.1 degrees. Well, now I've got one of my angles. All I have left is one more angle, phi. That's the only thing I need left. So how do I get it? Now I use my relationship about the angles. I know that theta plus phi should add up to 90 degrees. Well, theta is already 53.1, plus phi is the thing I'm looking for is 90. So all I have to do is take 90, subtract off the 53.1, and I get 36.9 basically as my phi. And now I've successfully gotten all the missing information from my triangle. I started with some information. I used a whole bunch of relationships I learned from trigonometry, and I'm able to solve for all the unknown stuff. Every single problem you do will be similar to this. It's just, what is your starting information? In this case, we started with two sides, but maybe I start with a side and an angle, or different things. So let's try another example and see how it would work.
Can I ask a question before you go?
Yeah. What's up?
So this is like more of like a general question, but in my math classes in high school, we were told to round to 3 decimal places. Are you a stickler about that?
No.
In your class? Okay.
No. In this class, what I'll say is this. It is important to know the rules that scientists use to give their data. And that rule, the set of rules that they use is what's called significant digits or significant figures. I guarantee you, if you take chemistry, they're going to force you to use significant digits. And it's to get you into the habit. And it is important, and if you ever go into the real scientific world, then you better give your data in that form. Because if you try to give more decimals than you should, then you're going to wind up getting incorrect answers because you're assuming more information than you actually have. However, for my purposes, every time I teach a course here, I don't worry about it. And the reason is because, first, I know everybody sees significant digits in some other class, so they get the rules somewhere. But more important is, I want people to less focus on that formality and worry about how they put their answer in correctly than the actual physics that they're learning. So concentrate, for my classes, concentrate on the physics, calculating out a right answer. How many decimal places to give? It depends on the problem, but usually 2 decimal places, 1 decimal place is sufficient for me to see that you got the right answer. If you round too much, then I can't tell if you did it wrong or not. And then if you just write, 15 decimal places, that's just a pain in the butt to have to do. So no, long story short, I don't demand any specific rule of giving the answer other than generally 1 or 2 decimal places is perfectly fine for me.
Okay, thank you.
Sure. All right, so let's try this one. Here's a triangle. Okay, let this be 10, this be 30. Here's x and here's y. Here's my 90 degree. And this will be theta. And so for this one, find x, y, and theta.
I'm not sure if this is just on my screen, but it's frozen for me.
All right, let me restart it really quick. All right, so here's my triangle. I want to find these 3 pieces of information. So very similar. All we have to do is we know what tools we have to use. Now we just want to figure out which ones should we use. So first thing I can ask myself is, can I use Pythagorean Theorem? And in this case, not yet at least, because if I tried, what I would get is something like x squared plus y squared equals 10 squared. Well, that's fine, except there's 2 unknowns sitting there. And math has proven to us that you can never solve for more unknowns than the number of equations. So I can't use Pythagorean Theorem yet. I may be able to later, but for now, no. What else do I know? I know the relationship between angles. Can I use that? In this case, I can. I notice I have the 90, I have a 30, and then theta is what I'm looking for. And what I know is that if I add all these together, I better get 180. And so if I do this, I get theta equals 180 minus 120, which tells me theta must be 60 degrees. And so this happens to be another one of those fancy special triangles, and it's called a 30, 60, 90 triangle. If you have a right triangle, and one of the angles is 30, then you automatically know the other angle has to be 60, because 30, 60, 90. All right, so there we have one piece of information. Now what about these sides? Well, we can't use Pythagorean Theorem. We already used our angle, so the only thing left is Sohcahtoa stuff. Sine, cosine, tangent. So let's say I want to solve for x. What do I know about x? Well, x can either be thought of as the side adjacent to 30 or the side opposite to theta. So I could use either one. But like I said in the last problem, because I solved for theta, I can't be 100% sure my number for theta is correct. So I'd rather use the 30 just to be safe. So I know I'm going to use 30, and I know x is adjacent, so I just think, okay, is adjacent sine or is it cosine? Sohcahtoa, the ka part, tells me adjacent goes with cosine. So I'm going to say cosine of the angle 30 is equal to the adjacent side, which I'm calling x, divided by the hypotenuse, which is 10. And there's my equation. Now I just need to solve this for x, so I want to get x by itself. So this becomes x equals 10 times the cosine of 30. And if I plug this in my calculator, I get 8.66. Now remember, if you are doing this on your calculator, we will be using degree mode for our class. I know in math they like to make you use radians, but for our purposes we're using degrees. So make sure you're in degree mode to get the right answers for these things. So now I have x, I have theta, all I need is y. At this point, again, I have options. I could use now Pythagorean Theorem, or I could continue to use trigonometry, or the sine cosine functions. I'll show you both. My preferred way of doing it is with the trig functions. So if I'm looking for y is the side opposite to 30, and I know from Sohcahtoa, opposite goes with sine. So I would say sine of 30 is the opposite side, which is y, over my hypotenuse, which is 10. So get y by itself. Y is 10 sine 30, which is 5. And there we go. Now let's say I wanted to use Pythagorean Theorem instead to find y. That's doable. Pythagorean Theorem would say x squared plus y squared equals hypotenuse squared. So what do I know? Well, I know x is 8.66. Of course, that's rounded a little bit, but so 8.66 squared plus the y squared, which is what I'm looking for, is equal to the hypotenuse squared, which is 10 squared. And so now that's my equation sitting there. I want to solve this for y. So I bring the 8.66 over. I get y squared is 100 minus 8.66 squared. And again, I don't like the square on my y. I want to get rid of it, get y by itself, so I take the square root of both sides. So this tells me y is equal to, and I just use my calculator because I don't know 8.66 squared, 100 minus 8.66 squared, and then I take the square root, and I get 5.0004, whatever. So of course you get the same thing. You should. You should, as long as the numbers you're using you calculated correctly. Had 8.66 been calculated incorrectly and I got 15 or something because I did something wrong, then obviously using Pythagorean Theorem is a bad idea. But there you go. There's another example. Here's a triangle. Some information is given, some is excluded. You want to use your relationships to figure out all the missing pieces. And like I said, it's kind of a puzzle. You have tools of solving the puzzle, It's just that the problem doesn't tell you which tools to use or when to use them. And the more you do these, the easier and quicker you get with them. Are there any questions about this? All right, now, what we're going to do next time is we're going to, I think, start with vectors. I'm going to start introducing vectors. How does trigonometry relate to vectors? And we're going to spend a lot of time on vectors. And the reason is because vectors is the most important topic for you to get right from the very beginning, so that the rest of your career, your school life, your physics life, engineering life, will be much easier. As I said, almost all of physics deals with using vectors to solve problems. All of engineering is using vectors to solve problems. In fact, the textbook, when you take the engineering course, Statics and Dynamics, it's called Vector Mechanics. So it tells you everything about it is vectors. And we have to see how to use vectors, how to manipulate them, what's the algebra of vectors, what are the operations, what's the math behind it. And we have to get very, very comfortable. I have a lot of experience both as a student, but also as teacher, that has told me the place where students make the most mistakes in physics is doing the vector parts of things wrong. And just as an example, what we'll be doing is you'll be given some information, like how far you leave your front door, you walk 20 meters at an angle of 30 degrees north of east, and then you turn and walk 5 meters at an angle of 60 degrees west of north. And the question is, from your front door, how far away are you? And in which direction? That type of problem is solved by vectors. We turn each one of those operations you did, walking out a certain direction and a certain distance, into vectors, and then we add the vectors. And when we add the vectors, we get a new vector whose information is the answer to the problem. And what we're going to find is adding vectors is not the same as adding numbers. Adding vectors takes more complexity. You have to do certain things to the vectors before you can add them. And that's the step where most people get things wrong, because you have to figure out, do I use sine of the angle or do I use cosine of the angle? Is it going to be positive? Is it going to be negative? And if you don't know this trig, and specifically the fundamentals of vectors, very, very, very well, then you'll get mistakes in that part of the problem before you even do the physics of the problem, before you even add in any equations or anything. So I choose to spend more time than regularly done to focus on vectors, so that you'll become experts with vectors. That way, when you get to General Physics 2, Modern Physics, every other physics you take, you'll already know vectors very, very, very well, and so it'll be a breeze. Once you know vectors, physics becomes a lot easier. If you're rusty in vectors, then you'll find out you get problems wrong a lot and you don't know why you're getting them wrong, or you don't see why you're getting them wrong. So we're going to focus a lot on it, and that's what we'll start next time. Also, I will be posting a homework either today or tomorrow on this math review stuff. Just a couple of problems that you would do and then turn it back in on Canvas. I'll talk about it, of course, next time. And I will email when it's posted to let you know. Generally, let's say I post it today. it wouldn't be due until either Friday or Monday. I give a number of days to do the homeworks. So, but just look out for that. When it's posted, I'll send an email, so look out for your email. But other than that, any questions for me on anything we've been going over so far?
For that homework, you check homework for completion or accuracy?
Both. I do give partial credit, so
Okay.
it's not like, oh, you got it wrong, completely wrong, the whole problem
Yeah,
is gone. No, I give partial credit, just like I would for tests. Yeah.
Yeah. So, like, based on, like, the work that we do, if some of it is good, they go, like, gotcha.
Right.
And then you said degrees instead of radians.
Yeah.
So we're going to okay, that's we. Okay, cool. Okay.
Yeah, for the purposes of our calculations in this class, I don't think we're ever going to worry about radians on your calculator. There will come a point where we're talking about rotational motion, where the units we use will be radians. So radians per second is how fast you spin or something like that. But in terms of actually working out a problem on your calculator to get a number, leave it in degree mode.
Always in degrees. Gotcha.
Yeah.
Thank you.